here we go. Hey, Sparkies. I'm talking to the future. You're listening to the past. Of all the chapters that I could have picked to go on with our next topic, given our current circumstances, I decided to go with chemical engineering because the individual chapters do not necessarily rely on each other, which is really cool. So, my question for you guys, and I'm going to put that up as a discussion thread later on this week. How have chemicals influenced our society? I mean, all of you guys had chemistry, many of you had it with me, and we've talked about all kinds of things. But chemical engineering, that's a different one. So, again, the discussion topic would be how have chemicals influenced our society? Okay, now I'm going to flip over. All right. So, in looking at our objectives, there's a lot. I'm only going to go over the first three today. You are going to define what is chemical engineering. You're going to compare and contrast chemistry and chemical engineering. How are they alike? How are they different? Okay. You're also going to explain the laws of thermodynamics and how are they actually used in chemical engineering. I mean, we've talked a little bit about it in chemistry. If you had me for physics, we did talk about it in physics, okay? And if you have AP chemistry, then yeah, you really got into it, okay? Nothing like thermodynamics. Okay, I'm going to skip down to the next page, and here we go. So, chemical engineers. Basically, these are people who work with large-scale production of chemical products. They're the ones who help run the factories, the manufacturing plants, and the examples that I'm listing there, that's not all of it. I mean, food products, fertilizers, medicines, household cleaners, paint, cosmetics. You can also create, synthetic materials for shoes or clothing or whatever. Okay. So there's an awful need for chemical engineers and definitely chemical engineers who work in the cosmetics business. That's a major moneymaker for them, especially if you got a master's or a PhD. You literally could punch your own ticket with that. Very, very important things going on out there. So for chemical engineers, they also invent new processes. They design, they build, they operate facilities. Now, that's a diagram of making, I think it was nitrogen fertilizer production, which again, what do we use fertilizer for? Well, to improve crops. Huh? Yeah, absolutely. So, looking at new processes, I mean, if you think about our current news now, apart from, yes, we got the coronavirus, but we've got people trying to work on vaccines, desperately trying to find a vaccine that people can take that can help them fight the coronavirus. Well, guess what? There's some chemical engineering involved in that too. And it won't be just making the vaccine, developing the vaccine, it's also being able to manufacture it in large quantities that we can get it out to people. That's the general idea. Any questions? Oh, seems like I'm talking to myself in the office here. My door is shut, no kitty cats. Sorry, guys. Now, if we look at chemists, on the other hand, they're working more on the smaller scale. They work in labs, they work with chemicals on a smaller scale, and I gave an example of microscale chemistry. That is an actual term. And if you look at this picture here, you may notice this particular thing right here. And you might think, where did I see that before? If you had me for chemistry, you may remember we did a precipitation lab. We had tiny little dropper bottles, and you were mixing all these different chemicals to see if you were going to have a positive reaction or not. Like it would turn white and cloudy. Okay. Holy cow, it's white and cloudy. Holy cow, it's white and cloudy. Okay, I'll stop. Weird Al forever. I'm just saying. So, but chemists also, they create chemical reactions. They do a lot of development for things. So looking at predicting the products here, for example, this is what chemists do. I got to go back on the microscale chemistry here. Why do we even bother to do something on such a small scale? Well, for one thing, you're generating less trash, less chemical waste. Because chemical waste, we got to talk about disposal, and that will be another topic for another day. And you're thinking, wait, this is AP Environmental Science. Yeah, that's where you got some connections going in there. That's true. But here, the idea is that you use less resources, you're generating less waste, and you're still getting the same results. So whether you're using a few drops of something or you're using, a 1 liter beaker for something, you're still getting the same results. You're just getting a lot less waste. It's more practical, okay? Cleanup is easier, and guys, it saves on the money. There's an economic benefit to it as well. Okay, let's move on here. Professional aspects. Well, you know what? Bachelor's degree for entry level positions. There's a chemical plant there for you. An associate's degree can lead to a technician's job. Okay, pretty much with an associate's degree, it's getting your GE, maybe take a few classes in basic chemistry, and that could, you could go apply for a job and become a technician, and they would train you, and that's pretty much it, which is true for a lot of technician jobs out there. There is the American Institute of Chemical Engineers, that's true. Chemical engineers, of course, they need to be ethical, honest, and there's also teamwork and communication skills that would be kind of important. And again, where's the source of all ethics? Well, it's the Bible. It absolutely is. And it's really important, especially for chemical engineers, to have ethics. That kind of knowledge is very dangerous. If you think about it, yeah, let's not. Let's move on. Let's look at some chemical engineering principles. We're not going over all of them today. We're just going to look at chemistry and thermodynamics. Okay? That's it. Where is mass balance and fluid dynamics and deformulation, which sounds really kind of cool. Okay. Let's go into chemistry. Woo, trip down memory lane, and some people are saying, "Oh no, 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 not stoichiometry, please." No, I promise there's no stoichiometry here. There isn't. Okay? Scientific study of materials, their composition, their structure, their properties, their interactions. Hey, what happens if I mix sodium with chlorine gas and I light a match? Things like that. The changes that these chemicals will undergo. We've talked about like chemical changes, for example. Okay, what happens when you're putting in electricity in a tube that's filled with neon gas? Well, the neon atoms, they glow because electrons are excited, they jump up and down, they get energy, they go up levels. When they go down, they're releasing the energy like a hyperactive kid on a sugar rush. Yeah, exactly. Okay? So, yeah, that's kind of chemistry in a nutshell. And some people are thinking, wait, a year? A full year of this, and that's how you're summarizing chemistry? This is an engineering class, not chemistry. You want chemistry? Go back. Okay? But the way I look at it for chemistry, unless you're going into AP Chem, you only need to do Chem once. That's it. Okay, so looking at that, now we'll move on to thermodynamics. Thermodynamics, I've covered a little bit of it in chemistry. I also covered it in physics, which tells you that there is an interconnection in between a number of the sciences, like chem and like physics. There's a lot of connection there. So you're studying the work and the energy and the efficiency in large-scale systems. Okay, so we can talk about machinery, for example, or we can talk about a chemical process. There's thermodynamics involved in that. Now, there are certain laws that we have that will predict how things are going to work, like the first law, second law, third law, and the zeroth law. The zeroth law, I never called it that, but I talked about the idea definitely in physics with that. All right, let's move on here. So, first law of thermodynamics, okay, law of conservation of energy. Energy cannot be created or destroyed. Hey, isn't that the same thing as the law of conservation of matter? No, because matter and energy are two separate things. But it is an important thing in our universe that we do have a law of conservation of energy and a law of conservation of matter. Otherwise, our universe would be seriously falling apart, and there'd be so many of God's natural laws being violated on an ongoing basis, it would be frightening. Okay? Pardon me, I got to get my caffeine break. Watered down tea. Woo. Okay. So the amount of energy in a closed loop remains constant. Loop. What do you mean by loop? Think of it as a system, okay? You have a system. That's what they mean by a closed loop. If something from the outside of the system comes in and messes it up, then the first law of thermodynamics, you can't really hold that you can't hold that to be true. Because let's say I have a chemical reaction that's happening, right? It's going great, but all of a sudden I decide to kick it up a notch and I add more energy into it. Okay? Well, the amount of energy in the closed loop remains constant. That's just it. I add extra energy, that's not true anymore, and therefore the first law is not going to apply in that situation. Now, energy may be changed into another form, but the key thing is it is not destroyed. That's just it. It'll change into other forms. You burn gasoline, okay? You get some exhaust, you get a bunch of heat, right? And heat is a form of energy. You have the engine that's burning the gasoline, it's making the drive shaft turn to make your car go, right? That's mechanical energy. So this is an example of chemical energy being changed into mechanical energy, heat energy, and well, yeah, that's the smelly, dangerous stuff you don't want to inhale called exhaust. That's just nasty. Okay, first law of thermodynamics, pretty straightforward. Second law, I like to call it chaos. The professionals hate that term. But in other words, entropy is a tendency of all energy or matter to seek a state of uniformity. The idea is everything is the same. Like a lot of pop songs we hear today, it's the same. Same hook, same tempo, same timing. Hey, if you don't believe me, check it out yourselves. So, entropy is a tendency of all energy and matter to seek a state of uniformity. What do you mean by uniformity? Where everything is the same. Okay, so when you look at something like this diagram here, okay, you have here high randomness, high entropy, and high disorder. Okay, if we go this way, we start to increase. We cut down on the entropy, we cut down on the disorder, we cut down on the randomness. Okay, and then further and further to the point, this is where we end up. Okay, so that's what happens. That's one way that the you can go from an area of high entropy to an area of low entropy. And that you can look upon that as matter. That's one way to look at it. Personally, I like the energy aspect of it, where you have a lot of energy. You start out with a lot of energy. You wake up in the morning, you're full of energy. It's summer, okay? And you're going to go out, you're going to do stuff with your friends and all that. And then by the time you're reaching your bed at night, you're very low energy. You're tired. You can't think very well. You're confused. And you're like, I just want to crash. That's it. That's entropy. Okay. High entropy is when you want to crash. You're tired. Ugh. low and having low entropy where you have high energy. That's when you wake up in the morning, you're feeling refreshed and you're saying, I want to live. Okay. Second law, again, concentrated sources of energy naturally disperse. And some of you guys might remember this little picture. I had to get it back from Kim to put that in there because I think that's the best visual for entropy. Now, you look here, you notice there's an S here. In chemistry, and I didn't do that in baby chem, and I did certainly do that in AP chem, S stands for entropy. Okay, so the entropy of gas is greater than the entropy of liquid, which is greater than the entropy of solid. That's it. It's all that it is. Okay. Third law of thermodynamics. I really don't talk about that a whole lot, but I mean, I don't call it the third law of thermodynamics, but in chemistry, we did talk about it's called absolute zero. The energy level of an object is based on how much the atoms move. Now, there is no atomic movement near temperatures of absolute zero. That's where they say atoms don't move one bit. We've gotten to way less than 1 degree Kelvin. And what the physicists and the chemists are seeing is that matter is starting to behave in a weird way. It's like, this is not normal. What do we do? But we haven't gotten down to absolute zero yet. So that's still a mythical point, but it takes a lot of energy to suck the heat out of that material. Okay? Think about it that way. So that's the third law of thermodynamics. Think about absolute zero. How about the zeroth law? Sounds weird, okay? Essentially, it's an observation looking at thermodynamic equilibrium. I did talk about thermodynamic equilibrium in physics, okay? Now, what would that look like? In physics, we talked about the idea about the amount of heat that an object has and the temperature that an object has, and we would do calculations with it. I mentioned it a tiny bit in chemistry. So I have two boxes here. Actually, you know what? Let me get the other one. And there's a future miniatures project I've got going. Okay. If you want to know, ask me later. So these are two boxes. They are the same size. Okay. Now imagine one happens to be 25 Celsius and the other is 26 Celsius. Okay. So one's a little warmer than the other, not by much. Now the idea is this. When they come together, okay, heat goes from a warmer object to the cooler object, right? It's a pretty important idea. So this has got 26 and this is 25. When we put it together, they're going to come to what's called a thermodynamic equilibrium. Okay? What does that mean? It means that the energy and the temperature would be the same here. Now, I bring in my third box here. It's got a little another future project in there. Okay? This one has more. Let's say these two are at 25.5 Celsius and this is at 28, okay, Celsius. When we put it in contact like this, okay, and that's where you're seeing the diagram ABC, you're seeing the three objects being in equilibrium with each other, a thermodynamic equilibrium. Because remember, when they come in contact with each other, the energy is going to move around, the heat energy, to be specific, is going to move around until all of these are equal with each other. And it doesn't matter the size. It's the idea of thermodynamic equilibrium. So that's the zeroth law. In other words, when objects come together, okay, they are going to, if they come in contact, given that the outside is the same temperature, but the objects have slightly different temperatures, when they come together, they will even themselves out. That's what they mean by the zeroth law. Okay? Not a typical thing there. Okay, so at this point, ladies and gentlemen, we have talked about thermodynamics. We did talk about the zeroth law here, thermodynamic equilibrium. We looked also at the third law of thermodynamics, looking at absolute zero. We looked at the second law of thermodynamics, looking at the wonderful thing of entropy. Okay. And then we looked at the first law of thermodynamics, which practically everybody and their mom knows about that one, right? Law of conservation of energy. We also looked at the idea of chemistry, what it is in comparison to what chemical engineering is. Okay? So we looked at that, and there's definitely different things. Chemical engineers work on a much larger scale. They work on projects, they build, they design, whereas chemists are the grunts. They work with the, day-to-day, let's pour stuff in the beaker type thing. So their job, the nature of their job is different. Chemical engineering is pretty important because with it, there's a lot of things that are made that wouldn't be here today. And for that, ladies and gentlemen, we've accomplished our objectives here today. Okay, looks like I didn't do too long, but at this point, ladies and gentlemen, I will go ahead and I will upload this to my brand new YouTube channel. Okay, all right, you guys take care, God bless, and have an awesome day.